Hi, everyone. My name is Sierra. I'm one of the MS advisors within the ECE department. We're just going to wait a couple of more minutes for everyone to come into the meeting, and they're maybe still in another meeting. But today we will be taking a tour of Professor Feynman's lab, and then you all will be able to ask questions at the end. Thank you. Okay, let's just get started since we only have 20 minutes. So I'm going to go ahead and play a tour of Professor Feynman's lab.
The Ultrafast and Nanoscale Optics Group is an integral part of the Applied Optics, Photonics, and Nanoscale Devices and Systems programs of the Electrical and Computer Engineering Department at the University of California, San Diego. The research group is directed by Professor Shia Feynman. Current research areas include broadband wavelength selective filters, integrated microwave photonics, CMOS-compatible nonlinear metamaterials, integrated nonlinear processing, nanoscale lasers, brain imaging, and integrated spectroscopy. This lab space is used for spectral characterization of photonic integrated circuits in a fiber and free space-out configuration. This setup uses a set of two 4F optical systems to filter and magnify the collected output optical mode. This is a versatile way of characterizing a variety of on-chip devices and systems, and is a powerful tool utilized for analysis of devices and prototyping. This setup is used for characterizing second and third order nonlinear susceptibilities by the Maker's fringes technique. In this setup, the input optical polarization state is controlled via a wave plate, and the output power is measured in both the P and S polarizations. This is a powerful method of characterizing optical nonlinearities. This lab bench is used for spectral characterization of photonic integrated circuits in a grating in, grating out configuration. This setup serves a similar purpose as the first setup. However, it uses a grating coupled configuration, which allows measurement of more densely packed on-chip devices by removing the need for access to the edge of the chip for coupling per device. This is an alternative to the first lab setup and is also very versatile. This lab bench is used for S-parameter characterization in all four primary configurations: electrical-electrical, electrical-optical, optical-electrical, and optical-optical via an optical network analyzer. This is a powerful tool primarily used when sensitive characterization of high-speed devices is needed. This tool is often used to characterize modulators and detectors. For more information, please visit ece.ucsd.edu.
I hope you all enjoyed that virtual tour of Professor Feynman's lab, and he is actually here to answer some questions. So if you all have any questions, feel free to put them in the chat and I will be reading them, or you can unmute yourself and ask via Zoom as well.
So I have a question. I was wondering what projects do you envision potential students that are be coming in the fall? What projects would they theoretically be working on, at least in the near future?
Well, it's a good question. I have no idea. It all depends on your guys' interest. You saw what we are doing. So we have some active research in nonlinear optics on a chip to generate some new sources. In other words, there are lasers that are hard to build from semiconductors. So one idea is to use nonlinear wave mixing, convert the wavelengths, and most interest is in going into long wavelengths. And the long wavelengths is very challenging because you need now to support many different parameters of very distinct frequencies with wavelengths that are not really comparable. Just as an example, if I want to use 1 micron or 1550, and I want to generate 5 micron, it's factor of 5, right? So now whatever was single mode becomes multi-mode for the shorter wavelengths. So how do you handle it? So that's kind of work that we are looking right now. It's a mixture of nanotechnologies, somehow mode engineering, or some people like to use word sciences. Dispersion engineering or dispersion science is still an open question. There are few parameters. You can mix materials, you can mix geometry. There are few possibilities, and if you guys are familiar a little bit with nonlinear optics, there is a issue of matching the phases of the multiple frequencies, which is not trivial. So all that is kind of challenging projects that we are currently investigating. We also look at very small lasers. What we want on a long run is to be able to phase log them, because each emits very little light. And if you go to the far field, you add them up incoherently. Now, if I phase log them, then I will get power densities n squared versus n. If n is large, it's a big number. So that's another project that we are currently kind of exploring. And of course, in silicon photonics, we want to build spectrometers on a chip. So we did some work in the past. There are a few papers in the pipeline, in submission, review, whatever. And the spectrometers is also a challenge, have to make the whole thing on a chip, including the source, right? Because if I want to do interrogation, the whole idea is make a spectrometer that I can put in a cell phone. And then I go to the supermarket, somehow it detects if the fruit is ripe or the meat is fresh or the fish is already ready to go to the garbage can, right? So these are kind of things we are looking at. Let me think one more time. We have ongoing plasmonics research, but right now it's not, it's mostly focused on biosensing. We are trying to estimate composition of DNA mixture, not sequencing, just to determine what is the concentration of the 4 base pairs in a string of DNA. And this is very useful in figuring out if certain medication works or it doesn't work. So you take a sample and see if the concentrations came to normal or they are still kind of messed up. So, and this is, the goal is make it simple, compact, that you can maybe put it in the cell phone. Today, everything should be in the cell phone, right? Any other question? That's very general. I gave some details, but if there are concrete questions, I can elaborate. Any questions, guys? I see like 23 guys and everybody is silent. So I'm ready to go and bail out. There's no point to.
Professor, I've got a question then. How do you see, or how has your group adapted to working in a like social distance environment? And do you see that continuing in the fall? How are you guys handling that?
Oh, we are handling it very well. I have a virtual whip on the graduate student, okay? So clearly we are not having, now this is a joke, a bad joke maybe, but it is what it is. So we are using Zoom all the time. So we spend quite a bit of time and on as a group. The group is run like different topics. We have subgroups, but everybody can participate in every other group. So these are literally like you're asking a question concrete to COVID. I'll give an overview. I like to talk. You mentioned you figured that much out, huh, Dominic? So in any event, so we have weekly meetings. So we have some work we have on plasmonics, on silicon photonics, and the nanolasers. And now we also have a couple of meetings that are project oriented. So for example, there's some of the funding coming from agencies that require quarterly reports or bi-monthly reports, which is a pain, but we need to keep running to have something to report, right? So we keep this focus group, few students from even sometimes different groups get together to discuss this progress in specific project. So these are two combinations, one programmatic, science-oriented or area-oriented, and the other one is project-oriented. Not too many because we need to leave some time to do some work, right? Can't keep talking all the time. So that's about it. I would say it's maybe 5 hours a week roughly on me, okay? On you a little bit less probably. Then we have one seminar meeting on Wednesdays that everybody gives a seminar on an exciting paper, whatever the paper is, right? It's your choice, but it has to be in detail and so everybody can learn something new. Okay, so that's also part of the deal. So COVID didn't affect any of this, right? Except we can't touch flesh, right? It's all virtual. Now, regarding your specific question, how do we cooperate with COVID? It's a pain, 25% occupancy, but the students go into the lab one at a time, okay? So some labs have some setups that many students need to use, so they share. They say, okay, I was a pain. I was saying, well, there are 24 hours, who cares? You can sleep in daytime and work at night, right? So, well, it doesn't happen, of course, but people are kind of partitioning, saying some people wake up early in the morning, so they take the morning shift, and some people sleep in, they take the afternoon shift. So let's say 8 to 12, 12 to 4, and then 4 to 8. There are night workers too, right? So we somehow handle this type of complicated setups, and one of the setups you've seen in the video, one was at the very beginning. Alex was showing it, and then he was showing the chip scale testing lab in the CalIT building. So there are two setups to test the chip scale silicon photonics, like circuits, different kinds. I forgot to mention, we also tried to build spatial light modulators in silicon using the same CMOS fabrication. By the way, in silicon photonics, we use tape outs. We reduce the amount of fabrication in Nano 3. We have facilities. We used to do it everything there, but now with the COVID and many other reasons, whatever can be taped out, we tape out. It becomes more time efficient, and also economic. The latency is about 2 months from some foundries. So that's more or less what we do. Now the Nano 3 labs, the fabrication labs also open. They also have some restrictions, but we follow the rules on one hand. On the other hand, it's not completely shut down. It's slowed down a little bit, but I wouldn't lose sleep over it because also some of the projects rely heavily on modeling, simulations, and design. So this, we just bought a new computer system that runs COMSOL, the finite element simulations, much faster. It's state of the art as opposed to our old system that was 2-3 years old. So for example, if something was running for a week, now it runs 1 day. So that's an improvement, 7 times faster, right? So that's about it. We do also, some students like more analytic work, so they do some analysis work in the designs, and that's about it.
We have about 4 more minutes until the next lab session, so maybe time for one more question.
So what kind of materials does your group look into for nonlinear effects?
Well, we look, even if my blood is nonlinear, I would use it, but we have some advantage in the sense that we looked at silicon nitride many years ago. We have experience with silicon nitride for the past, I want to say, maybe 15 years. And one of the first papers on nonlinear wave mixing on nonlinearity in silicon nitride was done by one of my former students who is now in Japan, a famous professor. So recently we figured out that another of my students, she went to Singapore, is also a famous professor, and she started to do silicon nitride rich of silicon. So you can push the stoichiometric silicon nitride with index of 2 to about 3 point something. So it's close to silicon. Now, the higher the linear dielectric constant, the higher the nonlinear coefficient. So this is this silicon-rich nitride, but in fact, it also has inherent Chi2 coefficient. We are trying to understand why. It shouldn't, because it's supposedly amorphous, shouldn't have a dipole, but it does, and it's still something that we are investigating. So. And of course, we can always, we are now looking at lithium niobate on SOI to use for nonlinear wave mixing. I forgot to mention, we have one project on quantum where we are trying to build a generation of entangled photons on a chip, but it's still under the umbrella of nonlinear optics. So. We are reviving what we did in quantum cryptography back in the mid-90s. So trying to revisit it again, became very popular. So anything else? Because I think I'm going to run in 1 minute out of time. Ciara is watching me, right?
Yeah, there's another lab session starting at 3:50. But if you all don't plan on going, and if Professor Feynman has the time, maybe we can do one more question.
I have plenty of time. The night is young, right? But I don't want to distract you guys from your following the schedule. So with some of you, I will be meeting separately. So if you have more questions, you are welcome to write them down and or email or show up at the meeting, whatever.
Thank you, Professor. Have a good day.
Good luck to you guys. Enjoy your virtual visit.
Thank you, Professor Feynman.
My pleasure anytime.